Yeah, the previous class we were talking about the RAFT algorithm. So in that, the first one is any node in that network, they will be in any one of these three states. One is either they are the followers, or second one they become the candidate, and third one they become the leader, right? So initially, every node or every server in the cluster, they become the followers. They try to listen the network. Is there any information, updated information is there or not? That means any leaders are there or not. If not there, then they wait for a random period of time and then they try to send a request to become as a leader. And for that request, if majority of the cluster servers they sends the response, then the request will be committed and given as a leadership. And after that, leader will take care of creating the log replications, and that log replication will be shared among all other cluster servers. Okay, so that is what we have observed in the previous class. So what is the importance of this log replication, or how the log will be built by your leader so that it will be sent to all other users in the network? So in the previous case, we have seen that there will be server 1, server 2, the server 3, server 4, and suppose server 5. Then if server sends a request, that is the request out, with the term number, suppose term 1, if everyone is having the term 1 here, then that request is broadcasted among other users in the network, that is with the term number, that is a request out with the term number 1. So that will be received by many other users in the network. So based on that, whatever the response comes from this, the servers for this request, then the server 1 will become the leader. The condition here is every server in this network, they have to respond to only one request, not many requests. That's the condition. So that if the every server is committed to this server, then the server 1 become the leader. So after become leader, what is the job of this server? This server will get the request, or if any new transactions or commands are issued by any of the client, right? So that client transactions will be received by your server 1. I'm trying to prepare a log replication in that entry, and that log replication will be the broadcasted to, or information will be shared to all other users in this network, right? So the leaders, they accept the client commands. That maybe like in the previous example we have seen, the Z client is going to update with number 6, like that. So then append them into the log entries as a new entry. If the previous log entries are there, suppose like X is having some 5, Y client is updated, suppose Y client is updated, suppose 6, your Z client updated, suppose 10, and any new entry, suppose having some client A is having the entry, suppose 6, then your server the leader will receive this transaction or client and trying to add it into the existing log. So as soon as trying to add this in existing log, it goes through this, the new entry will be broadcasted to other users also. Once every user makes this entry, append to the log replication, then that the new log replication will be given as an input to your state machine or replicated state machine. Then that state machine will execute that log replication. It executes, and once it is executed, that will be treated as your committed, the committed log at that term point. Okay, so then the leader issues the append entry RPC in all parallel to its followers, and then apply the entry to their state machine. Once it has been safely replicated by all the majority of your servers, then that will be executed by state machine. So once it is executed, that is committed, and that reply is given by your leader to the client, to whoever issue this entry for the client, answers that your entry is successfully added to log file. So what is the basic structure of this client request and the log that we'll discuss? So as we said, the client sends a request to the leader here. So in the leader machine, that log will be maintained. In that log, whatever entry is there, that will be added. And at the same time, that log is broadcast to other users. We call the follower 1 and your follower 2. Okay. Upon receiving this, the followers also try to update that log in their log record by appending. Okay. Once it is appended, the servers, the followers respond to your leader that yeah, we made the entry. So followers source that request in their log entry, and once this acknowledgement comes from these followers to your receiver, the leader, then they try to execute that entry with the state machine. Once it is executed, that means majority of followers accepted that, and they compared with their log entries. It is matching, so new entry is executed by your leader, and that acknowledgement will be given back to your client that your the new entry or new command is added successfully to the log file. Right? So this is the basic job of your leader which happens. So now we have seen that in our example, suppose server 1, server 2, server 3, server 4 and server 5 is there. Server 2, server 3, server 4 and server 5. So then at term 1, if your server 1 becomes the leader, suppose, then server 1 creates the server 1, server 2, server 3, server 4 and server 5. Then server 1 become the leader, so server 1 needs to create the log record. So how this log organization happens means it is having the log index and maintain the log term. You call this term 1, term 2, term 3. Okay, and the entry which is requested by your client, this x equal to 3 or y equal to 1, your y equal to 9, these are the entries which are requested by your client to the server 1 or your leader. So in this case, you can find that whenever the leader appends the new entry, that will be announced to other servers or other followers. These are the followers in this case, right? So now tell me from this figure, do you think that who is the leader of your term 1? Who is the leader of the term 1 in this case?
It should be because a leader only commits once they've received something from the majority of their followers, right?
No, during the time, suppose S1 is there, in term 1, S1 become the leader, suppose.
Yes.
Because how it is elected means that we have seen in the previous slide, right? So from this diagram, tell me for term 1 who is the leader during term 1.
Oh,
You have five servers: server 1, server 2, server 3, server 4, and server 5.
it seems like server 1 and server.
Right? Yeah, server 1 is the term leader. Why? Because by just observing the number of log entries up to the log index 3, majority of your server 1, 2, 3, and server 2, 3, 4, and 5, they appended their entries here, and from here it is clear that these are all the followers. Right? Now, you can see the difference here. Your log entries of your server 2 is completes at the log index 5. Log entries of your server 1 is complete at the 8th index. Log index, the maximum log index of your server 3 is also 8. Maximum log index of your server 4 is of 2 in the log replication, and log index of your S5 is 7. Correct? Now from this you tell me why this inconsistency is there in terms of your log replication.
The failure to communicate, or just errors in system 4.
That's one point. Any other points? Why there is a log inconsistency? When we talked about the RAFT algorithm, we say that all the servers are trustworthy. Okay? But there is a fail mode or failure mode. It is because of the delay or because of the link disconnect. So after the second log entry, your server 4 is inactive because not active, maybe disconnected from this network. So that's why up to 2 entries there in the log replication of your server 4. Similarly, so for S2 was active or actively participated or received the log up to the log index 5 or up to term 3. After in term 3, after that your server 2 becomes inactive or delayed responding. So in that case, how to get the consistency of these log replications or log consistency? How to achieve this log consistency among these 5 servers? So the interesting thing here is the first server 1 is the leader in the term 1, and the server 2, server 3, server 4, server 5, they all are the followers. And because of delayed or because of the disconnection, few servers are updated their log replication, which is requested by your leader to update in their log file. So then when it is going to be commit, when this log is going to be given as an input to your state machine or state replication machine or replicated state machine. Because once it is executed by your state machine, That means the output of state machine gives your commitment, right? It gives the commitment. Means up to that the records are committed, are up to date. So in that case, you just recall that in RAFT says that when majority of responses received by your leader, up to that the log record is updated and executed by the majority of your servers to execute the state machine, so that that those records will be committed. So from here, now tell me up to which log index the commands will be executed by the state machine.
As long as we
There are 5 servers are there. You need to find the majority of servers should respond to the new entries. Yeah.
so long as we have uh, 3, in this case, 3 servers up, it should continue because of uh, because we need more servers on than off. So since we have 2 servers off, but 3 still active, we'll go until 7, and then once we get to where we have 2 at index 8, we should stop because we don't have quorum.
Okay. Any other from your side? So in term 3 also, your server 1 become the leader in this example, right? And server 1 received the commands from various clients, from client X, client Y, client X, another transaction, client X, another transactions. And as soon as your server 1 received these entries from the client X, they are added to the log file, this log file, okay, and that is the new log file is at the same time sharing with the other servers. So here at this point, at term 3, leader is your server 1, and having the more entries up to log index is 8, but very few servers are active at this point at log 8. So majority of servers who are active in this log index means up to 7, majority of your servers, that is your server 1, server 3 and server 5, they are active, correct? So out of 5, 3 are active, that means majority of servers are active. So the new log file which is going for your commitment entry is up to log index 7, up to log index 7. Okay, so later on after the log index 7, if this server 2 and server 3 gets reconnected to your network, then they are going to, at index suppose 8, if they are reconnected to network, they are going to update this log file from the leader that up to 8 they are having the entries. All these entries will be appended or updated. This is we call the replication. So with this what happens? There is a safe and liveness is there in the blockchain, permission blockchain, which achieves the liveness and safety of your blockchain. So if any user goes down or any user gets enabled again, but the as the network time is going on and growing the record, the new distributed ledger is always updated by any the users. So sometimes they are inactive and sometimes they are active. Okay. So this is the important, the organization, log organization and its importance. Then comes to how it maintains the consistency in the record means the RAFT log matching property will be there. So what is that? If two different entries, suppose server 1 and server 2, if two different entries, two entries in different log, the log of your server 1 log and your server 2 log, okay, the two entries of two different with the same index. So what is the index here? The index is given like 1, 2, 3, 4, 5, 6, 7 and 8. And server 2 is having the index of your only 1 and 2, which is what we have just considered from server 1 and server 2 here, right? In that case, the how it is going to be updated means the entries stored in the same command that will remain same, and all the remaining entries will be find out who is the leader at that particular time. If server 1 is the leader and the new commands are there inside their log entry, they will be appended here. So it says if two entries in different logs have the same index and term, these entries store the same command. Same command. That means x is equal to 3 and y is equal to 1. Here is also x is equal to 3 and y is equal to 1. Okay. That means if index and term is matching, then they have the same command here. So we call the first one is, this is 1, 2, 3. It shows your index. And your 1, 2, these entries are your term, in which term they were appended, and these entries are the commands, or we say the transactions. Okay, so it is simply matching if these indexes are matching, then they will have the same commands and same entry will be there. Okay, so that is how to append the entries when there is an inconsistency check as compare your S1 and your S2. Okay, so from this it says that when there is a leader trying to send a request to the followers for appending a new entry, which is this new entry from the from a client, your y, that entry is your y is equal to your 1. So then for in terms of inconsistency check, your leader will send the index and term along with this new entry, index and term. Which index? It is going to send the previous index and previous term plus your new entry before doing the commitment to this one, that will be sent. So upon this request received by your follower, the follower will check the index, that is 3, and the term is 2. When the previous index and previous 2 is matching, means the record is up to date and the new entry will be added to it successfully to maintain consistency. If the the leader is sending the previous index and previous term plus your new entry, this new entry, okay, upon receiving this request by your follower, the follower will check with the index and the term. When the term is not matching, your follower rejects this entry. Follower rejects that entry. Okay. So then in this scenario, you just tell me what happens. Your follower is getting the entries, the inconsistent entries from the network, claiming that the term is 1, which is by the leader, and the new entries are j is equal to 2, y is equal to 6, a is equal to x, and so on. So from here it is clearly assumes that these entries are fake entries. These entries might be sent by the malicious node or any of the attacker. So to make the consistency in such cases, your follower is comparing the term first. So that means here the leader is saying that second term also I am the leader for creating the log. And in the second term, I got the entry or command from a client X is equal to Q with the index 3. So then here it is a mismatching. So how to solve this mismatching means? Because your follower is simply rejecting this. Follower thinking that the leader is a fake leader. So in that case, your leader, what it do? It adds its previous term and previous index along with the new index and new entry. So that time from the previous index from 2 to 4 index plus the term is 1, 2 and 3 new terms are added plus the new entry. So upon receiving this by your follower is going to check the term which is requested from your leader. The term is matching with the index 2. Then check the command whether the same command is there or not. If same command is there, q is equal to 8 and q is equal to 8, then your follower accepts that request, okay, and replace all the other records from that point onwards and updates the log file in its one. So that is follower after the update of this consistency. Am I clear here? Okay. So that is the appending entries consistency check. First consistency will be checked, then the entries will be added. So once it is committed here, now that means in the follower also the log file is up to the log index 4, and in your leader log replication also up to index 4, then this log replication will be executed by your replications state machine, which is there in this server, leader server, and this will be independently executed by the replication state machine. Then it will give the output as you are committed. It is committed. That means up to here the log records are up to date. Up to date. Okay. So this is the append entries in inconsistency. But why? Why this raft means the raft commits the entries in the strictly sequential order. So with this, how it is helping? The entries in the log record are up to date. If any fake log records comes, those fake log records are simply removed from the log replication. And at any term, every server in the network that maintains the same log entries. Same log entries. So this requires, this raft commits entries are, requires the followers to accept the log entry appends in the same sequential order. They cannot skip these entries. So there should be a consistency. So it is a greatly simplified protocol compared to your Paxos. Okay. Only thing is, first the leader selection is happening, and then the second one is your log replication, or your replication of your log will be done. And this replication log will be done based on the term, index, and the command, or we call the transactions, simply transactions. So with the help of this replication, it will also identify the fake entries, okay. So that is why this raft commits to, the raft is bit easier for implementation than your Paxos. Okay. So let us see this handling the slow follower. As we saw in the previous case, your server 4 is a slow follower than your server 2, 3, 4, and 5. In that case, how it is going to be maintained? Replication. So leader reissues the AppendEntry RPC to the slow followers. So they are the idempotent. How? We'll see that. Whatever the committed entries are there, that is up to date of term and your index. Okay. So these are executed by your state machine. So then it becomes your committed entry in the log file, right? Log, which consists of your the term and entry as well as the transaction. Correct? So it committed entries guarantees to both the durable as well as eventually execute by all the available state machines, those who are active at that particular time. Correct? So committing an entry also commits all previous entries, as we just saw here. Committing that. So up to here, at term 3, index 4, the log is committed, executed by state machine. So all these previous entries are safe. So the safety rule by your FLS will be achieved by following this concept. So the committing and entry also commits all previous entries up to date. So there will be a safety. There will be a safety as well as your liveness. Safety as well as liveness, because the majority of servers, those who are active, they are still doing, competing for the leader. Then once they elected as a leader, they're trying to create the replication, log replications. So liveness is also there. So all the append entries of your RFC, the remote procedure calls, that includes the heartbeat, and that includes the index of the most recent committed entry. That means what? This heartbeat entry indicates the other servers, as we said, server 1, 2, 3, 4, and server 5. So as soon as this heartbeat entry received from these servers, your heartbeat entry or heartbeat message received from this server by other user, they comes to know that server 1 is live. The server 1 is alive. That means server 1 is not get down or not disconnected from the network. But in the random period of time, if server 2, server 3, server 4, other servers, if they are unable to receive this heartbeat message, the RFC message, that means it indicates that either these connections are disconnected or the server may become slow. The server may become the slower one. Okay, so this will be there. So these entries, your heartbeat entry, index, term, and command. Okay, in the log file, in the request file, the request of your log consists of one is the heartbeat message. So this indicates your server is active and having the index of the log, then term, what is the term of that, and having the command. Okay, so in that request log file, this information will be there. Upon receiving the request log by your server 2, server 3, your server 4 and server 5, they first go and check whether heartbeat message is there. If there means server is active, and then based on this index and term, they check whether the log record is up to date or not. If it is up to date, then the command or the transaction will be appended in their log files and then start executing by your state machine. So in this, the handling the leader crashes, suppose if leader goes down, then how to handle the network. So this algorithm gives that the leader can leave the cluster in inconsistent state if the old leader had not fully replicated the previous entry. So that means some followers may have in their log entries. So in our case, if log S server 1 goes down, then the remaining two servers, server 3 and server 5, they are alive. So server 3 or server 5, between them, anyone become the leader, and that leader log replication will be again shared with other servers, those who are active by that time, so that they can update their log files to that time. So some followers may have their log entries that the new leader does not have. So in that case, the other followers may miss the entries that the new leader has. So then new leader will update new leader's log file by collecting from your followers. Yeah. So this is, in this case, see the log index from your 1 to 10. Your leader become the leader for term 8, suppose, or sorry, for the index 8, the become entry. So here you can see the server A, B, C, D, E, F. So here the possible followers are the A, B, C, D, F, and is the leader here. So the new entry which comes here, suppose leader 1 goes down. That means what? Your leader left the network with inconsistent data, correct? So then from these possible followers, anyone can become the leader. When anyone can become the leader, then they try to get the new log file from every user here. Then check what is the majority of followers having the same index, same term, and same command. So from that point onwards, your new leader is trying to add the new entries. So here you can see the leader, term 1 leader, get the transactions from different commands, from different clients, and those transactions are broadcasted among all other users. So they have updated that log file up to index 3. So then in the second term, your leader F become the F become the leader in the second term. Okay. So here in the second term, F become the leader. So F received these 3 what you call the entries are commands from the client, and this command is trying to in the second term, your F trying to broadcast these entries with the other users in the network, but before broadcasting, your the server F become inactive. That's why you can see in all other followers, there is no entry for your term 2. So after that, the F got the become as a leader for in the term 3, but didn't receive any transactions, and those transactions are not shared with any other users because leader become crashed there. So again, that will be inconsistent. Only F is having term 2 and term 3 transactions or commands, but none of other the servers are having the transactions here, right? So then at term 4, again your this server become the leader, and they broadcasted that the term and the transactions to all other servers here. So those who are active by that time, they updated their records here. Correct? So then in this case, your server term at term 4, this server record is updated by your A, B, C, D and E, but not by your F. Okay. So then at term 5, again this server become the leader, new transactions are added, that will be added by your A, your C and your D, but not by your E and F. So in this case, how it is going to be handled? That the log status after the election will be handled by whatever the maximum commitment is there, that will be selected here up to index 6. It will check what is the maximum the users, they have the same index and same term. So out of A to F, your leader, the up to index 9, if you see the server A, your server C and server D is having the updated information. So up to here the log record will be maintained. If any new users come and join, then they will get this index term 1, term 4, term 5, term 6 and their transactions will be added. Right? So this is what, when a leader at the top comes to the power, it is possible that any of this scenario from A to F in this case could occur in the following logs. That is, each box represents one log entry. The number in this box is your term, as just mentioned. So the followers may be missing the entries from A to B, or may have the extra uncommitted entries in C and D, or both in E and F. So in the scenario when F could occur, if that server was the leader for term 2, as we discussed, that added several entries to its log, then crashed before committed any of these terms. Because this term is, during the term 2, F is broadcasted all those entries to this, but before going to execute by your state machine, after execution of your state machine, only these records will be committed. So before committed, your F become crash. So in that case, what is happening here quickly? So it restarted quickly and become the leader for term 3 and added few entries in the log before any of these entries, either term 2 or term 3 were committed. So server crashed again and remained down for several times. So in that case, the other server, your server A, become the leader for 4th term or 5th term, and sixth term your server C become the leader, seventh term server D become the leader, right? So an election starts as the server goes down before the commitment. So the log information will be shared with the other state machine. So candidate for the leader position that request vote for other former followers to become. Okay, so that includes the summary of your state of its log. What is the log status and what is the term and what are the new entries are there in that. So the farmer forward the replies with the new index, whatever the available index is there. So the farmer follower compares the state of their logs with the credentials of the candidate and vote for the candidate unless their own log is more up to date than the leader's log. If they have already voted for another server, then they can simply reject for the new request from this leader collection. So handling this leader crashes in another way is the RAFT solution is to let the new leader to force the followers the log to duplicate its own. That is another one, third way of solving. So that conflict the entries in the followers log will be overwritten. So how it will be done? The new leader is in charge. So the new leader is forcing all other followers to update their log as per new leader's log. So this is third way of solution. Finding the consistency in the log. Yes, please.
So that this would then run the potential risk of a server being offline for a while, having the capacity outdated. It joins right as the current leader drops. It becomes leader, and then all of the progress made while it was off is just overridden.
Yeah, that is the case. There again, the new leader, when new leader is selected, it's same case it happens.
Okay.
Yeah. So newly elected candidate force all other followers to duplicate in their log or content of its own log. So how new leader is going to selected then? Possibly, if he is very active, then only there is a possibility of selection. Yeah. So how it is means the leader maintains the next index for each follower and index of entry it will send to that follower, and new leader sets that index to the index just after its last log entry. So the 11 in our previous example, the 11th entry in this example, this 11th index entry. So here the leader D become the leader here, and at the 11th index at term 7 he become the leader and forcing all others that A, B up to F. Everyone, this new leader is forcing to replace their log files. That means what? The leader who is very active in the network become the new leader and having the most updated log entries will force all other followers to follow the same index. And then it broadcasts it to all the followers to follow that file. So the followers that have missed some append entries calls will be replaced. Like for example, in this example, the follower, suppose F is a follower when D become the leader, then F try to replace all the entries right from your term 2 to term 3 with the entries of your the D server up to this. So there will be a complete replacement. Yeah. So this is what the replacement process that is we have seen. If A is the leader, suppose, then ask the B to replace all the entries or add all these entries. So because by successive trials and errors, leader finds out that the first log entry follows B will accept is long entry of your 5. That is there is a long entry here. There are, one entry in the term 4, two entries in term 5, and two entries in term 6. So this is the way of solving. So very interesting question comes from this discussion is, how will the leader know which log entry it can commit? So that means it can't always gather a majority, since some of the replies were sent to the old leader only. So fortunately for us, any followers accepting any accept entry RPCs, then the implicit knowledge has been processed with all previous followers. So followers log cannot be skipped the entries. So this the last observation from this discussion is, handling log inconsistency does not require a special in the sub algorithms to handle this. So rolling back entry append call is just enough for maintaining the up to date log replications. So this is the way. Because of this, your RAFT algorithm is much easier for implementation compared to your Paxos. Correct? So again, in this case, as we discussed, the safety is maintained because there are two main questions comes regarding this safety in the rafters, which we just addressed. What if the log of a new leader did not contain all previous committed entries? Then what is happening? It must impose the conditions on the new leader that your log entries are not up to date. We have the updated log entries so that it can replace you, and from there you start doing replication. Correct? And how to commit entries from the previous term means that is based on your previous index and the previous term, right? Yeah. If the index is that is what we have seen, 1, 2, 3, 4 entries are there for this term, for these entries. The term is 1, x is suppose 1, and your y is 1, and for this is term 2. Sorry, this is term 1. At this term 2, another entry is taken for index 3 is suppose z is equal to 3 suppose. And when this is announced, then for the follower, when receiving the follower, that is what we have seen, that when the follower is receiving that with the term 1 with the entries, and 2 with the entry, and with term 3 another entry is there, when that is announced, then your follower is comparing this term 2 with term 2. If it is matching, then this new entry will be added. If not matching, it simply reject that one. Correct? If this term 2 is also not matching, here is term 1 not matching, in that case also it rejects, then your sender, the leader is going to send these terms, right? 1, 2, 3 along with these indexes. So that will solve must tune the commitment mechanism. So how to maintain this previous entries means by following previous index and previous terms. So that solving the safetiness of your blockchain system, right? So in the election restriction, how it is going to restrict this algorithm suggests that the log of any new leader must contain all the previous committed entries. Because when sending the root request RPC, along with the root request, in that root request oath, the leader means that the candidate become the follower become the candidate. So candidate generates this this request oath. That request oath consists of all the previous entries plus the term plus index plus any these information will be there in this request out RPC. So upon follower receives this, follower first go and check the term, whether any new term or the previous term. If any this term newly requested term is less than any previous term, that means that request will be rejected. If the term is newly requested term is greater than any previous term, that means it is a new request. When it new request, the follower go and check what is the new index by this request out. When new index is identified, okay, then go and check whether the entries are up to date or not. If index entries are up to date, then the follower will reply to this request out. That means they give the grant. So that way the election will be done. If any term which is less than the previous one, that election will be restricted for that particular leader, the candidate. So before voting for that candidate, the servers check the log of the candidates at its least as up to date their log own. So majority rule does not reset. So that defines the up to date or the discussion. So we'll see that which log is more up to date. That means by comparing multiple requests, as we have seen that the cluster servers get the multiple requests. In that multiple request, when they compare with their existing log, okay, so which one is the updated one? For only that updated request out, they will respond. For all other requested out, they simply reject it. So which log is more up to date means if the log have last entries with the different term with existing one. If I am the follower and my log entry is my last log entry and the next entry from that request is different, then we treat that as your updated one. If not, we simply reject. The follower will reject. If the log end with the same term, and then whichever log is longer is more up to date. So that is what we have observed here. Forced to, okay. Here, when this request is broadcasted by this server A, then your server B will check what is the log entry, the fourth log entry. Then check what is the maximum log entry is there. If any other server, suppose this is another server D, is also announced this one. So which request is going to be considered by this server B? Up to log index 4, it's matching with the existing log and received two entries, request 1 and request 2 from two servers. Then it checks which one is having the longest log entries. So this server is having, D is having longest entry, so the D entry will be accepted. And the request which comes from A will be rejected. Okay, that is how it is going to be observed. That means which log is having more up to date, that will be accepted when having the multiple request votes. Okay, so the long entry for a term means the leader was elected by the majority of the servers. Okay, so the new leader will not erase the committed entries once committed. Okay, so that is if once any new entry is committed, no server has the right to erase those entries. So here it achieves the immutability. So as we said, your blockchain is a immutable. Correct? Yeah, so this is what we have just discussed, the election restriction in another way. The servers are holding the latest committed log entry and servers are having the elected the new leader. So then two majority of the same cluster must be interact. Their intersection should be there. So committing entries from the previous term means, as we said, majority of the what you call majority accepted log entries will be broadcasted and that will be taken as an entry. So all the committed entries from the previous term will be added to your new term. Okay. Yeah. So this is what we have so-called discussed the committing entries from the previous term means these are previous term are going to commit with the new term. So S1 is the leader here and partially replicates the log entries at the term your 2. So then going to when your S5 becomes the leader at term 3, okay, when your S1 crashes, your S5 is elected as your leader for your term 3 with votes from your S3 and your S4 and itself. So majority out of 5 majority votes got, so become the leader and accept a different entry at this index at the index 2 accept a different entry, then that entry will be broadcasted. Okay, so that is S5 crashes suppose and S1 restarts. In that case, which entry should be updated, whether term 3 entry or term 2 entry? So the elected when S1 restarts is elected leader and continues the replication of your 2, then which entry should be taken by these remaining servers. So your S1 again crashes, S5 is elected leader. Okay, then whatever the updated the term is there, based on updated term the entries will be replaced. So that is the committing the entries from the previous term, not from the previous index, is one way of committing the entries. Okay. Yeah. So, however, if again the S1, if S1 replicates an entry from its current term, suppose 2, on a majority of the servers before crashing, as the entry is committed by your server 5 in this case. So server 5 cannot win an election because majority of the server 1, server 2, server 3, server 4 and server 5, majority of the servers committed to entry 2, not to your 4, because here you can see the new entries which is received by your server 5 is shared with the other servers in the cluster but not committed. This ... say means not committed means what? Those entries are not executed, not yet executed by their state machine. Once they executed by state machine, then only it is committed. So here the broadcasted that information received by other servers, during that time your S5 become inactive. So because the server is unable to receive because inactive, so server not responding, or this S5 server is not responding for these responses. When not responding these responses, that server 5 is not yet executed the entry of your 3. So then whereas your server 1 later become executed the state machine of these entries, so those entries will be committed by all other servers, those who are active in the network. Right? So yeah, this is what the explanation which we just have discussed. So with this, I would like to stop this session. These are the ways which we have so-called discussed. So with this, I would like to stop the session.